So say you had a mass connected to a spring and that spring's tied to the ceiling, and you give this mass a kick, well, it's going to start oscillating. It'll oscillate down and up and down and up. But if I were to try to draw this, all those drawings would overlap. It'd look like garbage. Forget that. Let's just get rid of all this. Let's say we just drew what the mass's position looked like every quarter of a second. So this is what it started at. Wait a quarter of a second, now it's here. Quarter of a second, now it's here. So this is one mass. And we just took pictures of it, and we moved those pictures right next to each other. If I were to connect the dots, I get a graph, which is basically the height of this mass as a function of time. It looks like this. So if I were to plot this legitimately on a y or vertical position versus time graph, you'd get something like this. It starts at the middle and it goes up and then it comes back down, and this process repeats. And you know what this is. This looks like a sine graph. And in fact, if this spring is described by Hooke's law, and if you remember what Hooke's law was, Hooke's law said that the force that the spring exerts is equal to negative the spring constant times the amount that spring is stretched or compressed. Then this gives you the force, and if your spring follows this force, your graph would be exactly a sine or cosine graph. Now for this spring, it was a sine because it started here in the middle and went up. But if it started at the top and went down, you might describe it with a cosine. And if it's not a spring that's described by Hooke's law at all, then you might not get a sine or a cosine. But in this case, we're going to assume we have a nice spring described by Hooke's law. But here's my question. Let's say we didn't start the mass in the middle and give it a kick upwards. Let's say at t equals 0, we start the mass all the way at the top and we let it drop. In other words, we do this. We start the mass up here, we let it drop. The graph would look like this. This time, if we were to plot this over here, we'd get a graph that looked a little something like this. It would start at the top, then it would drop down, it would reach some lowest point, it would come back up, get up here. This process would repeat over and over and over again. My question is, are these graphs the same or are they different? Well, they're obviously different, but almost everything is the same. Their amplitude is the same. You know, they have the same displacement from the equilibrium. That's the amplitude. That's the same. Their period is the same. The period is the time between oscillations, so the periods are both the same. The only thing that's different is that one graph is shifted compared to the other. In fact, check this out. If I were to take this green graph, the initial one, and just shift it left, we get the exact same graph. They're almost exactly the same. One is just shifted, and so the word physicists use for this idea that two graphs can differ by the amount one is shifted is the idea of the phase. We would say that these two oscillators are out of phase. How out of phase? Well, one whole cycle would be from here all the way to there. They're not that out of phase. They're just shifted by this much, and that, it turns out, for this case I've drawn here, is only a quarter of a cycle. So you could say these are a quarter of a cycle out of phase, or if you think of the unit circle, we know 1/4 of a cycle would correspond to 90 degrees, either 90 degrees or pi over 2. And that's what these are. These are out of phase by pi over 2 radians or 90 degrees. But these ideas don't just apply to masses on springs. That'd be kind of lame if that was all they could handle. Turns out the much more relevant place where this idea of phase is important is for waves. If you had two waves, maybe two sound waves, or two light waves or any waves that could overlap, then the degree to which they're in phase or out of phase seriously determines how that wave is going to interact with the world. In fact, if they're completely out of phase, they can cancel each other, and that's as if the wave isn't even there. Or if they're completely in phase, then their contributions combine to form a more intense wave. And if they go from out of phase to in phase to out of phase to in phase, you can get an effect where the wave is intense and then it dies off, and then intense and it dies off. And so there's all kinds of situations where this idea of phase is important, not just in masses on springs. So how do we describe this idea of phase mathematically? Well, if we were to try to write down an equation for this green oscillator, say at t equals 0 it started there, I might write down that, okay, y is a function of time, the height of this oscillator as a function of time would be the amplitude, and remember the amplitude is the maximum displacement from equilibrium, so it would be the amplitude times, since this is starting at 0, I'm going to use sine because I know sine starts at 0, when t equals 0, of 2 pi over the period Remember, the period is how much time it takes to go through an entire cycle. This is the period. This is the amplitude. It's 2 pi over the period times the actual time. This little t is a variable. This little t represents the actual time at a given moment. So let's make sure that this equation actually works. If I were to start off at t equals 0 and plug in t equals 0 in here, the sign of 0 is just 0. So this whole thing becomes 0, and that's what I should have. I should start at t equals 0 at a y value of 0. So that's good. And then as t gets a little bit bigger, this inside amount gets a little bit bigger. The sign of a tiny positive amount will be a tiny positive number. So that's why this graph goes up from there. Eventually it gets to the peak. Where will it reach its peak? It will reach its peak when it gets through a quarter of a cycle. Remember, a whole cycle is this whole amount here. So a quarter of a cycle is just when it gets to the amplitude from 0. And that will be at a time t equals the period over 4. And the reason is that's a quarter of a cycle. Does this math actually give us that? It does, because watch, if I plug in little t, the time variable, as the period over 4, I'll get the sine of 2 pi over the period times the period over 4, because that was my time. The periods cancel out. I'd get sine of 2 pi over 4 is pi over 2, and pi over 2, that's 90 degrees. Sine of 90 degrees, or sine of pi over 2 radians, that's just 1. That's the biggest that sine can be. That 1 times the amplitude is going to give me a value for the height of the amplitude. This is going to describe my oscillator perfectly, since it's going to give what the height is at any given moment of time. So that wasn't too bad, but what do we have to change in order to describe the purple oscillator? So now I want to describe this purple oscillator. You might say, oh, well, easy, just make this sine a cosine. And yeah, for this case, turns out that works. But pretend like you didn't know you could do that. Or if you want to make it harder, say this was not shifted a perfect quarter of a cycle. Maybe it was only shifted like a ninth of a cycle. Then cosine is not going to do it for you. You need a more general way to adjust how much this wave is shifted. And that's going to be some sort of phase constant in here. Where do we put the constant? You might think, all right, if I take my green graph, I want to shift it to the left. You might think, well, should I subtract some like amount out here? That's not going to work. That's going to take your whole graph and subtract from the value you get for the height a constant amount every single time. Because of that, that will just take your graph and shift it downward. That's not going to work. If we added a value of b up here, that's also not going to work. That would just end up shifting our graph upward. All right, this b value is not going to do it for us. So you might want that in certain situations, but that's not going to shift the graph left or right. Turns out what we have to do to shift it left or right is add a constant within this argument of the sine here. So if I wanted to describe my purple oscillator, I'd say that y as a function of time is the same amplitude. Let's just again use sine. It would be 2 pi over the period times time. And then here's where the phase constant comes in. I'd have to actually add a phase constant. You might think subtract. You might think subtract because we want it to go left. Turns out adding a phase constant will shift the graph left. This was counterintuitive to me. This always freaked me out. I'd always forget this. How come adding a phase constant shifts the graph to the left? Well, watch. If we take this equation now, and instead of putting phi in there, this is the symbol we use for the phase constant in general, phi. And in this case, we know what it should be. It should be a quarter of a cycle, and for a sine graph, a quarter of a cycle is pi over 2. So let's just see if this works. At t equals 0, we used to get 0, which is what we wanted, but now for the purple graph, I need to start at a maximum value. So at t equals 0, this whole amount right here becomes 0, and I'm just left with sine of pi over 2, and sine of pi over 2 is 1. That's a maximum value, so times amplitude would give us the amplitude, which is what we want. We want a graph that starts at the amplitude. And this is better than just putting cosine, or at least it's better to know about, because now even if this phase shift was pi over 4, or pi over 9, or pi over 27, you could shift by any amount you want using sine or cosine. Now you know how to shift these things. You could turn them into each other if you want, or you could just shift them however much you want. Adding a phase constant will shift it to the left, subtracting will shift it to the right, and the larger the phase constant, the more it's shifted. You don't ever really need to shift it by more than 2 pi, since after you shift by 2 pi, you just get the same shape back again. So this constant in here, it's pi over 2 in this case. In general, it would look like this. You'd have some oscillator. It's got some amplitude. You could use sine or cosine, plus a phase constant. And this phase constant will determine how much this wave, or sorry, excuse me, how much this oscillator is shifted left or right. And I should say, be careful. Physicists can be sloppy here and use the same word for multiple things. Sometimes the word phase is used just for this little part here, this little added constant part. But sometimes by phase, people really mean this whole thing inside of here, this whole term that you're taking sine of, because this is what's determining where you're at in your actual cycle. And again, these ideas don't just apply to a mass on a spring. You could write down the equation for a wave. You'd have an extra term in here for space, not just time. And guess what? There'd be a little constant at the end that you could add that would be the phase constant. So this idea of phase gives you a way to describe how two oscillators or two waves are shifted with respect to one another, and it lets you account for all kinds of properties of wave interference that you meet when two waves overlap. Like we had for this mass on a spring.